Hello everybody. In this video we're going to talk about the limitations of DFAs. This is the first of two ways in which we can argue impossibility of DFAs. And this is a lemma called the pumping lemma. So we'll see what the pumping lemma is and how it can be used to show that particular languages are not regular. And the task of identifying that a language is not regular is not obvious. So far, we've seen various ways to characterize regular languages. So we are becoming pretty good in saying that something is regular, but saying that something is not regular is harder. So we have an example. We'll see two languages and ask if they are regular or not. The first language is D, which is all the strings W that have equal number of occurrences of 0, 1 and 1, 0. This is regular because we argued it in our last video. And we argued it through a wise way of restating this language and understanding this language. Now let's look at another language that seems pretty similar. So C, which is all W's that have equal number of ones and zeros. And this turns out to be not regular. So showing that the first one is regular wasn't obvious, but wasn't very difficult once we realized it. It took us a slide to kind of understand and how to look at this language. And then we had a regular expression that captured this language. So it wasn't very hard. Showing that something is not regular seems much harder. In general, the first question is kind of more algorithmic. Find an algorithm, find during finite automata that recognizes D. The second one is complexity theoretic. It's more about showing impossibility. Show that for every automata, the automata doesn't recognize this language. So it seems, and often is, much harder to show that something is impossible than something is possible, because to show that it's possible, you need to show me one finite automata. To show that it's impossible, I need to tell you something about all finite automatas. Still, we'll see now and in future videos that we have tools for finite automatas to argue that things are impossible. And this is one interesting aspect of finite automata, because it's simple enough. We understand pretty well what can, and also, as we'll see now, what cannot be done in it. So yeah, how can we show that no DFA exists? And the point is that surprising algorithms are discovered all the time. So just the fact that you tried and it didn't work doesn't necessarily say that it's impossible. So the first tool that will be very useful is the pumping lemma, and gives us some structure theorems about regular languages. So let's dive in and tell you what is the pumping lemma. The pumping lemma says that if L is a regular language, then there is a positive integer p. And we'll see where does this p come from, such that for all strings W in the language that are long enough, so W has to be larger than p, there is a way to rewrite W as the concatenation of three strings, W is X, Y, Z, with the following properties. First, Y is non-empty. The other parts can be empty, but Y is non-empty. Then the length of X and Y together is at most P. And finally, and that's where the pumping comes For every I, the word X with Y repeated I times and then Z is in the language. So you can take Y and duplicate it many times, or even remove it because I can be 0, and you'll still have a new word in L. That's where the pumping comes through, because we take one word and we pump it. So W get pumped into longer and longer strings. But again, it can also be reduced in size by taking I equals 0. And this can be useful in particular exercises. So does this mean that any regular language is infinite? So after all, you take one word, you can create infinite number of words in the language. Is that what it means? Think about it for a second. Well, no. In fact, every finite family of strings, every finite language is regular, and you can easily build a finite automata that recognizes it, but by just trying to completely open up a tree until the length of the longest string and identify all the strings that are in the language. So how does it coincide with this lemma that tells you that you can take one word in the language and pump it to many other words? Well, the heart of it is in the fact that you can only do this if there is at least one word that is larger than this positive integer p. So in fact, for every finite language, the pumping lemma holds very trivially. You just take p, which is larger than every word in the language, and you'll get that the lemma holds vacuously, because there is no w that's longer than p. Okay, so that's kind of a confusion that I wanted to avoid. And now let's look at the proof of the lemma. It will be very short and simple, but yet the lemma is very powerful. It cannot show that everything that's not regular can be shown by the pumping lemma. It's not a characterization. We are going to see a characterization later on in the class, in the course, but it is very powerful. So let's look at the proof. L is regular, meaning that there exists some machine M, DFA, that recognizes L. And now we can define P, the constant from the pumping lemma, to be the number of states in M. Now let W be a string where W is in L, and the string is large enough. The string is larger than P. So what do we need to show? We need to show that W can be divided to X, Y, Z with the properties before. So Y is non-empty, X, Y are of size of length at most P, and X, Y to the IZ is in L for every I. So you can repeat repeat Y as many times as you want, or omit it altogether, and you're still in the language. So let's look at the calculation when you the path of calculation on M when it reads the string W. So you start with the state Q0 and you go through W plus 1 states, which is larger than P, because because W is at least P, so you have W plus 1 states, meaning that there exist at least 2 states that are the same. So here I'm just using the pigeonhole principle. If you are visiting in your path P plus 1, look at the first P plus 1 states that you are visiting. Since there are at most, there are P states altogether, P distinct states, there must be 2 locations where you are visiting the same state. So there must be J and K, such that Qj and Qk are the same. And in fact, well, J and K are distinct, are different, and K is at most P. Because that for this argument, we didn't need to look all the way until the last state, the last accepting state. It's enough to look at the first P plus 1 states. So you have Q0 up to Qp. There are 2 states within this range that are in distinct locations, but they are identical. And now it won't be hard to show the pumping lemma, given that. So let's reorganize our states a little bit. So we acknowledge the fact that Qj and Qk are the same states, and so let's just identify these 2 states to one location. And now the path from Q0 to QW goes through Qj. Then there is the path until you reach Qj again at location K, and then you go all the way to the accept. And this will let us divide the string W into these 3 parts. So X is the part until you reach this state the first time, you reach Qj. Y is the one that takes you from Qj to Qk, which is the same state. And Z is the one that gets you all the way to the accept state. And now we can verify the properties, all 3 properties of the pumping lemma. So first, Y is non-zero because Y takes you from Qj to Qk, and these are 2 distinct locations. K is larger than J. So, so the part of W that goes from Qj to Qk is non-empty. Then xy in joint length are at most of length at most p. This is true because, as we said, it's enough to look at the first p plus 1 states, all the states from Q0 to Qp, and these are visited when you look at the first p symbols of W. So within the first p symbols of W, there are 2 distinct, there are J and K that represent the same state, and K is still smaller than P, and XY reach all the way to QK, namely their length together is at most P. And finally, the fact that X, Y to the I, Z is in L for every L comes because you take X, and now let's say that you omit Y, you'll just continue to accept. You take Y once, you take this cycle once, and then you continue to Z. And you can take this cycle again and again and again, and at the end of each one of these times, you're still in the same state. So Z will still get you to accept. This comes, so the entire pumping lemma comes into this notion that DFAs, because they have a bounded amount of memory, they forget. So if an automata with enough states want to remember all the bits it read all the symbols it read at the first 3 steps or 10 steps, we can make sure that it remembers it. We can build a DFA such that after reading 10 symbols, you are in a unique state. So this state knows exactly where you've been at. But once you read more and more symbols, at some point, you're going to get into these loops, which means that you have forgotten. So when you're in this state, you cannot distinguish whether you whether you just read X, or whether you read X, Y, or whether you read X and Y 9 times. You don't have enough information to remember all that you've done so far. So DFAs forget, and they forget after a constant number of steps, and this is what we're using for the pumping lemma. Okay. I'll give you another version of the pumping lemma. It's not hard to prove, but it is useful in some exercises, so think about how to prove it. So again, we have a regular language, and there is a positive integer p such that for all strings a, w, b in L, where w is at least p, there is a way to write w as x, y, z with the properties that we had before. So y is non-empty, x, y is at most p, and a, x, y to the I, z, b is in L. The only thing that it says is that we don't necessarily need to pump the beginning of the string, the prefix. We can, for example, decide that we want to pump the suffix of a string or some area in the middle, as long as we are pumping a substring that is long enough, that its length is at least p. So you can try to look how to prove it. As a hint, when you take this computation and you go through W, you are going to encounter 2 states that are the same. In 2 locations, you'll reach 2 states that are the same, and then you can complete the proof just like before. So we know what the pumping lemma is. Let's try to use the pumping lemma. So let's prove that this other language that's very similar to the language that's regular, this language is not regular. So the language EQ of all the strings with equal number of ones and zeros is not regular. Let's try to use the pumping lemma to prove that. So by contradiction, assume that it is regular. Then there is some p, which is the integer from the pumping lemma. So there is some p for which the pumping lemma holds. We can define the string 0 to the p, 1 to the p. And this string is in the language. It is in equality, right? So 0 to the p, 1 to the p has the same number of zeros and the same number of ones. And furthermore, its length is larger than p. So this string satisfies the requirement of the pumping lemma and we should be able to pump it. Okay, we won't do it every time that we're going to use the pumping lemma, but I think once is appropriate. So we can write W as x, y, z with the properties of the pumping lemma. Y is non-empty, x, y is at most p. And for every I, every integer I, x, y to the I, z is also inequality. Now, because the string xy is at most, its length at most p, xy is entirely in the 0 part, in the first p locations which are all zeros in W. In particular, Y is an all zero string. So now, right, xy is at most P, and the first P bits are 0. So now when you look at the string x, y, y, z, you just added zeros. You didn't add ones, and therefore you have a string that contains more zeros than ones. And now you reach a contradiction. On one hand, this string is not inequality, but the pumping lemma would tell you that it is inequality. So this is a contradiction. We just as well could have used the string xz, which contains less zeros than ones, but both of them work. Okay, so I hope this was clear, and we'll give another example of a similar flavor. So let's apply it again. Let's look at the family SQ, which is actually an unary language. It is only over the alphabet that has only a single a character. It's only over the zeros. And the words in SQ are those zeros that are strings that are composed of some n squared zeros, where n is any non-negative integer. So the empty string is in SQ. The string with 1 0 is there, with 4 zeros, with 9 zeros, etc. So again, let's assume that SQ is regular. It means that there exists some P of the pumping lemma. And let's look at the word 0 to the P squared. So P squared zeros. This string is definitely of length that is at least P. It's larger than P. And therefore, the pumping lemma holds for it. And since the pumping lemma holds for it, you can write it as x, y, z, with y being non-empty. xy is of length at most P. And for every I, every integer, every non-negative integer, x, y to the I, z is also in, there's a typo here, is in SQ. So this means that x, y, y, z has to be in SQ. Now the length of x, y, y, z is p squared plus the length of y, because without y, the length was p squared. Without the second y, the length was p squared. We added one y, meaning that the length now is p squared plus the length of y. On the other end, the length of y is larger than 0 and at most p. So this means that the length of x, y, y, z is p squared plus the length of y, which is at most p squared plus p, which is smaller than p plus 1 squared. So it is of length larger, strictly larger than p squared, and strictly smaller than p plus 1 squared, and therefore it cannot be in SQ. And therefore it's not a perfect square, and we reach the contradiction. So although the pumping lemma tells us that it's in SQ, we show that it's not in SQ, and therefore our assumption that SQ is regular must be false. SQ is not regular. So this was a cool lemma that can be used pretty easily for many, many languages that are not regular. And fortunately, you'll have the opportunity of doing that yourself. Some parting thoughts. We've been using pumping for contradictions. We're taking strings in the language and we pumping them to other strings that are not in the language. And the two examples that we've seen have something in common, and this is that they are talking about counting. Counting that the number of zeros is the same as the number of ones, counting that the length of the strings is a square, a perfect square, and DFAs cannot do that. And they cannot do that because their memory is limited, and at some point they forget. And since they forget, they cannot separate strings that satisfy what you were trying to count or don't satisfy what you were trying to count. Thank you.